Good afternoon, sir.
Good afternoon, sir.
Good afternoon.
Good afternoon, sir.
Good afternoon. Check. Friends, can you able to see my screen? Is it visible?
Yes, sir.
Yes, sir.
Visible. Okay. Check. Okay. The other day we were talking about how to get information from a mass spectroscopy, then IR, FTIR, and C13 NMR and the H1 NMR. Based on that information, how to identify a compound. Okay, we solved one problem. Okay, this is solving a problem only. Actually, this problem is given in Silverstein, the author of this mm, book is Silverstein. The name of the book is Organic Spectroscopy. Organic Spectroscopy. Okay, problem number 822. Okay, a lot of problems are there. Okay, some problems are solved, some problems, okay, we have to solve. Okay, like this. Okay, see here, here, uh, the first picture, the first spectrum, okay, that is the mass spectroscopy. This one is a mass spectroscopy. Okay, then we did not study the mass spectroscopy so far. The next we are going to study after the completing the NMR. I will teach you the mass spectroscopy. The main objective of a mass spectroscopy is to identify its molecular weight, one thing. And apart from this, is there any, if there is any side group attached, okay, it will give an insight about the side group, what are the side group attached, okay. Say for example, if I take an aniline, the formula for the aniline is C6H5NH2. That is the formula for aniline, okay. Therefore, here the aniline is the side group here. And if you take toluene, CH3, CH3, this is the attachment here. And if you take phenol, the phenol will be OH, okay. And this mass spectroscopy will give an idea about what are the subgroups attached to the main thing, okay. And it will give an idea about the molecular weight, okay. The tallest peak in the mass spectroscopy, mass spectrum. Okay, if you see the there is a tallest peak. In the tallest peak, one number is given. Okay, see here the tallest peak in this case is this peak. Okay, and there is a number given 119. Most probably, this number will indicate the molecular weight of a compound. Molecular weight. Okay, the phenomena behind this mass spectroscopy is, okay, we are taking a mass, now we are taking a molecule, and that molecule will be bombarded with a high speed particles. It may be a charged particle, I think. Okay. Then in that case, what will happen? The mass will be split into different fractions. The entire molecular weight, that will be different, split into different fractions. Okay. The first, if you taken this aniline, this NH2 will be removed first. Okay. Then after that, this OH will be removed. Then after that, this CH6, the benzene ring, that will be disbanded. Then that will be divided into different fractions. Okay. This is what is happening here. Okay. And you'll be getting different fractions, so mass fractions will be getting. Okay. Based on the mass fraction, okay, which is liberated by fragmenting the entire molecule, you'll be getting different peak here. See here, first the molecular weight is 119, good. Then from 119, the mass is reduced to 91. That means a side group which is attached to this one, that is removed here. Okay. Then it is removed by bombarding a high energy particles. So okay, it may be in I don't know what is that exactly. I will tell you what is that particle. Okay. Then by bombarding that particle, the extra attachment, like NH2 or HCH3, that is removed. Then after that, okay, some other extra particles may be removed. Okay, extra group, attached group, okay, that will be removed. Okay, then after that, finally I got one compound like this. Okay, therefore like this, I think it will be removed. Okay, Therefore, it will give an insight about what is the molecular weight of the compound and what are all the subgroups attached. Okay. From this one, what I can understand, okay, this the molecular weight is 119. Okay. See, I have been provided a molecule. Okay, I don't know what is that molecule, what is its molecular formula, what are all the groups attached, and my final objective is I have to elucidate the structure of the molecule. That is my objective. Okay, then I have been provided with a mass spectroscopy, then a FTIR spectrum, H1 NMR and C13 NMR, four different NMR, four different data I have been provided. Okay. Therefore, from the first one, I can understand the molecular weight of the compound is 119. Okay. Then this picture, the second picture at the bottom, that is the FTIR. FTIR. Okay. That is the Fourier transform infrared. Fourier transform infrared spectroscopy, FTIR. The FTIR is mainly used for finding the functional groups present in your molecule. Okay, this is based on the purpose of the principle behind that the FTIR is if if a molecule is subjected to IR region, okay, it is subjected to IR region of the electromagnetic wave. Okay, if you take an electromagnetic waves, okay, the complete electromagnetic wave can be divided into different parts. One is the gamma rays, X rays, then the IR, the UV visible IR, then radio waves, okay, then microwaves like that. It will be divided into different regions. When electromagnetic wave of this region, that is the IR region, okay, is passed over a molecule, then what will happen? There will be a vibration in the molecule. There will be a vibration. Okay. Therefore, based on that vibration, okay, there will be a resonance vibration will be there, and based on that resonance vibration, I can find out what is the functional group present. Okay. Therefore, this is the output of an FTIR, and there are some specific regions are there. If the resonance or if the absorption is at this point, okay, see here, here it is given as the wave number. Okay, therefore, if the absorption is between 3100 to 3300, it indicates the presence of a OH group. Okay, and if there is an absorption in the region 220 to 2300, like that. Okay, that may be due to the presence of a CM. Like that, there are specific absorption region for each and every functional group. Functional group, I mean, it may be an aldehyde, ketone, then amide, C triple bond N, double bond, triple bond, like that. N number of functional groups are there. Okay, based on the functional group, there will be a specific region in the spectrum, and it shows absorption on that one. Okay, therefore here, since there is an absorption spectrum, the spectrum will be somewhat ultra in nature. That is, there won't be any peak. Instead, okay, there will be a downward. This thing will be there. Okay, therefore this is absorption will be there. Absorption. Okay, therefore from this picture I can understand the given molecule contain OH group and the C triple bond N group. The C triple bond N group is called a nitrile group. Okay, nitrile. Okay, group. Okay, or cyanide. It can be called as a cyanide. Okay, therefore these two groups are present. Okay, that's what I can understand. Okay, from the FTIR. From the mass, what I can understand, the molecular weight will be 119. Okay, that's all. Okay, next, come to this one. Which one is a H1 spectrum? The spectrum H1 NMR. The H1 NMR always will have peak with the multiplicity. Peak with the multiplicity. See here, if you see this peak, there is a multiple. Okay, see this one is the 3. It is divided into 3. Therefore, this is the triplet. Okay, then this also a triplet, and at the peak also, and there are a lot of subdivisions are there. Okay, that is called a multiplicity. Okay, here is the 4 different types of protons. That's what I can understand. 4 different types of protons are there. Okay, type of proton, and this is another type, and this is yet another type, and this is one more type. Okay, but totally 4 different types of proton. It doesn't mean only 4 protons are there. It doesn't mean so. Only 4 different types of protons are there in the given compound. That's what I can understand. Okay. Now normally the aromatic proton, if you see, it is a aromatic protons are highly de-shielded protons. Highly de-shielded proton. Okay, that's why it is in the outer. That's why it is shown in the extreme left or in the left side of the spectrum. Okay, and the single proton like this, it indicate the phenolic proton. Phenolic proton means, what is the phenol formula? CH5OH, isn't it? CH5OH. The H which are associated with the O, that is called the phenolic proton. This proton, I'm talking about this proton. Okay. Therefore, OH proton, you look at the H associated with the O, that is called the phenolic proton. Okay, that will be shown here. Okay. Therefore, from this, what I can understand, one phenolic proton is there. Apart from this, 3 aromatic protons are present. Okay, that's what I can understand. Okay. The next comes to the C13 NMR. The C13 NMR can be identified with the help of a single peak. There won't be any multiplicity. Okay, this is the single peak. Okay, and second thing, there are first we will see this line. I am talking about this line. Okay, this line. Okay, in this, how many peaks are there? This is the peak number 1. All of you just listen here. This one is the peak number 1. This is the peak number 1. That is the one carbon. This is the second carbon. This is the third carbon. This is the fourth carbon. This is the fourth carbon. This is fifth carbon, and here one small carbon is there. Sixth carbon and 7th carbon. Okay, that means totally 7 carbons are there. Okay, from this one we have seen aromatic ring is there. That means in aromatic ring like this, one CN is attached. One CN is attached, and from this I can find out one proton is also there. Sorry, the OH is also there. Therefore, OH is present here. Okay. Then I have to check what is the molecular formula. How many carbon atoms are here? Okay. All of you wait. Okay. What is the structure here? The structure, the probable structure now. Okay. What we have predicted, the probable structure may be C triple bond N OH. That is the number of carbons equal to 7, isn't it? Okay. Therefore, 7 into 12, 84. Okay. The next number of hydrogens equal to 1, 2, 3, 4, 5. Okay, 5. This will become 5. And the number of oxygens equal to 1, that is 16. Okay. Number of nitrogens equal to 1, that is equal to 14. Therefore, totally 10, 9, 10, 9, 1, 9, 10, 11. Okay. Therefore, the molecular weight is 119. The molecule. All of you can able to hear my voice? Hello? Hello?
Yes, sir.
Students?
Yes, sir.
Here? Okay.
Yes, sir.
Therefore, the molecular weight is 119. Okay, that is what is shown in the this molecular weight. I can cross verify with the MS. Okay, see the molecular weight given in the MS. It is 119. The tallest peak only you have to take. Okay, the tallest peak will indicate the molecular weight. Okay, therefore the tallest peak in this case. Okay, I am getting the molecular weight of 119. Okay, that's all. Okay, from this I can identify. From this I can come to a conclusion that this is the molecule C triple bond N and OH. Okay. Now, the totally 7 carbons are there. Okay. The next, now what about this one? Okay. Therefore, I can predict the molecule is CH5OHCN. That is hydroxy benzonitrile. Hydroxybenzonitrile, that is the compound, hydroxybenzonitrile. Okay, but I don't know what is the position here. That I don't know. Is it orthohydroxy, benzohydroxy, or metahydroxy? That also I don't know. Okay, and next thing, the smallest peak. Okay, here there are 2 smallest peaks are there. 2 smallest peak. Okay, this peak is different. This peak is a highly de-shielded region. That is because of the C triple bond N alone. Okay. Therefore, this carbon is different. Okay, remove that one. Okay. Apart from this, we do have a small two small carbon peak. Okay, that indicate the quaternary carbon. Quaternary carbon means there is no hydrogen is attached to that carbon. That is the quaternary carbon. Okay, all of you can able to understand. Therefore, two quaternary carbon atoms are there. The next, apart from this, four other carbons are there. Okay, these are all the, if the peak is present here and here, and that indicates a methane carbon. Methane carbon means carbon with one hydrogen. Carbon with one hydrogen is called methane carbon. Carbon with one hydrogen, that is called methane carbon. That's all. Therefore, if the carbon is present in this and in this, if there is a peak corresponding in both these lines, in both the topmost lines, okay, that indicates the methane carbon. Therefore, I can understand, okay, four methane carbons are there. Okay, now again I will draw the picture. All of you just listen. Again, I will draw the picture here. The picture is like this, isn't it? Okay. The picture is like this. Okay. See here, Cn is there and one OH is there. And these two carbons are, it's a quaternary carbon. This carbon and this carbon are the quaternary carbon because there is no hydrogen is attached here. Okay. Therefore, this is called a quaternary carbon. The rest of the four carbons, definitely there will be a hydrogen attached to these carbons. Okay. Therefore, these carbons are called methane carbon. It's called methane carbon. Okay, that's all. Okay. Now, to some extent, I can find out what is that formula. Okay. The next day, my objective is I have to find out whether it is an orthohydroxy benzonitrile or metahydroxy benzonitrile or it is an parahydroxy benzonitrile. That I have to find out. Okay. Therefore, that can be predicted with the help of the number of protons, number of similar protons present. Number of similar protons present. Okay. Okay, let us see. Okay. See, all of you see here. Okay, let us take the first structure. This is the orthohydroxy benzonitrile. Okay, this is the metahydroxy benzonitrile. This is the parahydroxy benzonitrile. If you take a parahydroxy benzonitrile, this here one hydrogen will be there. Here, 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 here. Okay. Therefore, in the four lines, hydrogen will be there. Therefore, this hydrogen and this hydrogen are similar hydrogen. And this hydrogen and this hydrogen are similar hydrogen. And one more hydrogen is there. Therefore, here for this type, that is the parahydroxy benzonitrile, I will have only three types of proton. Only three types of proton. The meaning is I will have only three proton peak in the H1 NMR. In the H1 NMR. But I am having four proton peak. Okay, just to go to the see here, all of you can able to see this picture. Okay, see here how many protons are there. This is the first proton. Okay, see here. This entire set, that belongs to the first proton. The entire set belongs to the one type of proton. This is the second type of proton and the third type of proton. And apart from this, here one more type is there. Therefore, totally you are having four different types of protons are there from the spectrum. Therefore, this picture is therefore what is this? The parahydroxy benzonitrile is not possible because here we are having only three types of protons. Okay. Therefore, this is what eliminated. Okay. The next we come to this picture. What is this picture? Okay. See here, this proton is different, and this proton is also different. But if you take this proton and this proton, these two protons are similar proton. Therefore, 1, 2, 3, and 4. Okay. Therefore, for the metahydroxy benzonitrile, you will be metahydroxy benzonitrile. You will be having four different protons or four different types of protons will be there. Okay. And see here we are having four different types. This is 1, 2, 3, and this is 4. Okay. Therefore, the probable structure will be metahydroxy benzonitrile. Okay. Let us check the orthohydroxy also. Orthohydroxy benzonitrile. That compound also we will analyze. We will check what is the type of the proton here. Okay. See here, and if you check this hydrogen, this is different. If you check this hydrogen, this also is different. But if you check these two will be the similar hydrogen. These two will be the similar hydrogen. Isn't it? Okay. Therefore, you'll be having 1 and 2 and 3. 1, 2. Let's check. We are having 4 different tables. 1, 2, 3, 4. Here. 1, 2, 3, 4. Wait, I will check. Okay, orthohydroxy. What is the okay, I will check this one. Okay, it seems that for orthohydroxy also we are getting 4 different people. Okay, I will check what is the reason for that one. Okay, then from the discussion, this is the meta-hydroxybenzonitrile is a possible one. Why the orthohydroxybenzonitrile is not possible? Why it is not possible? That I will check and I will let you know. Okay. Therefore, by this way only you have to find out how we have to elucidate the structure of the entire compound. Okay. The next example, we will go to the next example. Okay. See here. See, all of you can able to see my picture. Hello.
Yes.
Okay. See here. The molecular weight is 168. The molecular weight is 168. Okay. And second thing, the next peak is at 153. The difference between these two peaks is 15. Okay, that means one CH3 group is removed. Okay, the carbon atomic weight is 12, and 3 hydrogen you are having 3. That means the CH3 group will have 15 mass. Okay, therefore during this period, one CH3 is removed here. Okay, good. The next, if you compare these two, the difference between this one is 108, and this is, and maybe the CO2 will be eliminated here, and next CH3 is eliminated. Okay, therefore from this what I can understand, the molecular weight is 162, and there are some subgroups that which contain CH3, CO2 like that. Okay, and if you check the IR spectrum, the IR spectrum, the IR spectrum with the absorbance at 3000 spectrometer, that indicates, not spectrometer, 2000 at 3000 wave number, indicate the presence of an acid, and the C double bond O, that is the carbonyl compound. Okay, presence can be identified with the absorption at 1700 or 1750 in that range. Okay, therefore the molecular weight is 168, and it contains acid, and the C double bond O group is also there. Okay, that's what I can understand from these two. The next, see here, this is the H1 NMR. Okay, before going to H1 NMR, we will check the C13 NMR. Okay, see the C13 NMR here. What is the total number of carbons present here? 1 and 2, and this one is a 3 and 4, 5, 6, 7, 8, 9, 10. Totally 9 carbons are there. Okay, 10 carbons are there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 carbons are there totally. Okay, therefore whatever I circle, that is the quaternary carbons, because we know that the quaternary carbons will be smaller in size and very small inside, that too very dark, that indicates in the dark, that indicate the solvent peak. Okay, this one is the solvent peak. Okay, therefore what I can do, I can remove that one. The solvent peak I can remove. Okay, if you remove the solvent peak, totally you are having 10 carbons. Okay, the next, then among the 10 carbons, okay, we have to identify what are the different types of the carbons present that we have to identify. Okay, then see here, the 10 carbons I can identify in the bottommost spectrum. Okay, the next comes this spectrum. All of you just listen. I am talking about this spectrum. Okay, this spectrum. Okay, that too, which is some lines are facing downward. Okay, how many lines here? See this one, and this one, and this one, and this one. Okay, four different things are facing downward. That indicates CH2 carbon. That indicates CH2 carbon. Okay, therefore that indicates CH2 carbon. That also is solved. And second thing, in the last sample also we have seen that if we have a upward peak in this and in this, the upper two regions, okay, that indicate the presence of a CH carbon, indicate the methane carbon. Okay, therefore this indicate the methane carbon. That means only one CH2 group is there. Sorry, only one CH is there. CH carbon is there, and the four CH2 carbons are there, and the one which is facing upward, these two, but it is not having corresponding peak here. Here, it is not having corresponding peak, isn't it? Okay, that indicates the presence of a CH3 carbon. All of you can able to understand. See here, four different carbons are there. Quaternary carbon means in that carbon there won't be any H. Okay, then methane carbon means there will be one H will be associated. Okay, CH2, two hydrogen will be associated. In CH3, three hydrogen will be associated, isn't it? Okay, therefore the smallest carbon which is present in the bottommost spectrum, that indicate the quaternary carbon. Okay, good. And the dark peak, which is very small, okay, that indicates a solvent peak. Okay, that no need to take into account. Okay, that's all. And the remaining peak, it may be a mixture of a CH2. The remaining peak means the peak which is present in the bottommost. Okay, that is and after excluding the quaternary carbon, that may be the mixture of CH2, CH, and CH3. Okay, to find out the CH3, we have to go to the next level. We have to go this peak. I am talking about this peak. Okay, I am talking about this spectrum. In this spectrum, some lines are facing downward. All of you listen. Some lines are facing downward. Okay, but that carbons, that indicate the CH2 carbon. That indicates CH2 carbon. Good. Okay, and some carbons will have peak, upward peak. Good. It will be having upward peak in this line as well as in this line also. If you have upward peak in both the lines, that indicates CH carbon. Okay, and the left out peak, which are having peak only here only, the second spectrum only, but not shown in the third one. Okay, if it is so, those peaks corresponds to CH3 carbon. Okay, all of you can understand. Okay, therefore the number of carbons here, total number of carbons is 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Out of 10, 3 quaternary carbons are there. That is, quaternary carbon means there is no H attached. Okay, and one CH carbon is there. One CH carbon is there. Okay, therefore 3, 1, 4, and 2 CH3 carbons are there, and 1, 2, 3, 4, 4 CH2 carbons are there. That's all. Okay, let us see. Okay, this will be somewhat difficult for OZ and all. This is the okay. All of you, whatever you are seeing, this is called a 2D NMR. 2D NMR. Okay, and that is not including your syllabus. Okay, it will be very difficult to understand also. Okay, we just leave it. Okay, then finally see here the number of carbon atoms of quaternary is 2. Methylene is a CH2 like this. Okay, from this I ultimately found the picture. Ultimately I got the picture like this. Okay, this is the picture. Okay, that is the compound name. See, 1,3-dimethyl-4-methylene pentenyl ethanoic acid, or okay, it is a very long, very lengthy name is there. Okay, 1,3-dimethyl. That is, in the first position and the third position you are having one methyl group, and at the point 4 you are having one methylene group, and it is an ethanoic acid. Okay, therefore this is such a big formula. Okay, therefore like this one, you have to identify the picture. Then this picture is a two-dimensional 2D NMR. Okay, therefore, okay, let's give that overall picture. Okay, I think this is sufficient for you. Okay, therefore I will ask you. Okay, sometimes what I will do, I will give you a C13 picture, and I will ask you what are the C13 and the H1 NMR picture I will give you, and I will ask you how many CH2, CH3 and quaternary carbon atoms are present, and how many protons are there in this picture. Okay, you have to tell. Okay, that may be the question. Okay, then all of you can able to understand. Hello.
Yes,
Hello.
sir. Yes, sir. Yes, sir.
Okay. Okay, we will be some more points. Okay, with this we will conclude or we will finalize this one, and I will send all the material. Okay, through your Google Classroom. I will send. Okay, you have to go through that one. But the problems I will not ask anything. Any problem will not be asked because it is an objective type question only. Okay. Yeah, okay. All of you will go to the other day we were talking about the H1 NMR, I think. Then some of the points related to the C13 NMR, it is a C number. Okay, with that we will finish. Okay. Then we will go to the MS. Next class we will start the MS. When is my next class? On Wednesday, isn't it? Tomorrow. When is my, all of you, when is my next class?
Tomorrow, sir. 11 to 2.
Tomorrow, isn't it? Okay. Tomorrow we will start the MS. Okay, wait. All of you wait for some time. I will change the slides. Students, can you able to see my picture? Hello? Can you able to see?
Yes, sir.
Yes, sir.
What is there in the slide? Can you read? Can you read?
Introduction, sir.
Proton NMR spectroscopy, spectrometry, isn't it?
Yes.
Okay. A few more points are added in the proton NMR spectrometry in this file. Okay, see here, nuclear magnetic spectrometry is absorption spectrometry. Is there any different spectrometry other than absorption? Yes. Emission is also there. Okay, so sometimes what will happen before the absorption and the emission, the meaning is the electromagnetic waves, the nature of electromagnetic wave. Electromagnetic waves means it will have both the electrical component and as well as magnetic component, and they will be right angles to each other, and the direction of propagation will be right angle to both the component. Okay, electrical and the magnetic component. Okay. And if you pass an electromagnetic wave on a substance, then what will happen? Some substances will absorb, some substances will emit. Okay, like it. Okay. Therefore, the spectrum we can divide into two things. One is the absorption spectrometry, and other one is the emission spectrometry. This is an absorption. Okay, when an electromagnetic wave in the region. Okay, different regions are there: gamma region, X-ray region, UV visible, IRA, radio frequency, then microwave, different regions are there. Okay. Here we are going to use the radio frequency region of the electromagnetic wave. We are going to use when that radio frequency wave is falls on the substance, that will absorb. Okay. Now, absorption is a function of a certain nuclei in the molecule. It is a function. Function he means the nature of the nuclei. The nature of the nuclei again can be classified based on the spin quantum number I. Okay, if it is having even number of a proton and a neutron, then I is equal to 0. In that case, it is not NMR active chromophore. If it is odd and even number of a proton and a neutron, then it will be the I value may be half, 1/2. Sorry, not 1/2, half, 3/2, like that it will be different. Okay, and sometimes we may have a whole number also. Okay, the NMR spectrum, x-axis frequency of absorption peak and y-axis peak intensities. Okay, absorption frequency, the absorption frequency, that absorption frequency only we are going to convert in terms of the chemical shift. We check the definition for the chemical shift. We check the definition, the frequency of the signal minus the frequency of the reference divided by frequency of the signal, frequency of the reference divided by frequency of the equipment, isn't it? Okay. Therefore, that you are going to convert into ppm. That's all. Okay. All nuclei carry a charge. In some nuclei, this charge spins on the nuclear axis. If you see here, it's clearly given. This charge is, what the charge present in the nucleus, that is a proton. Okay, that will spin about the nuclear axis. Okay, this circulation of nuclear charge generates a magnetic dipole along the axis. Magnetic dipole. What do you mean by magnetic dipole? Magnetic dipole means positive and or south and north pole will be created. Okay. Angular momentum of the spinning charge can be described in terms of a spin quantum number. I can take a value. The spin quantum number can take a value 0, 1, 1/2, 3/2, 5/2, and so on. Okay. Then the spin quantum number determines the number of orientation that we have seen. M is equal to 2e plus 1. Okay. And we are concerned with the proton whose spin number I is equal to half, because the nuclei with the spin quantum number I is equal to half, that is easily affected by the external magnetic field. Okay. Therefore, the nuclei with the spin quantum number I is equal to half, that is more often studied in NMR. And the examples for the value of I, and they have given some examples for all these things. Okay. Say for 0, that is C12O16, and for the case of the other thing, that is of 3 by 2, 5 by 2, okay? That is H1 C13, F19, and P31 like that, okay? Okay. The natural abundance of the H1 is 99.9 percentage, and the C13 is 1.11 percentage only. And if you take F19, it is 10 percentage, and the phosphorus is also 10 percentage. Okay. The energy difference between the two different spin levels are given by del is equal to gamma H B0 divided by 2 pi. Gamma is called a gyrometric constant, gyromagnetic ratio. Okay. And the remaining things are just a constant, and the B0 is the applied external magnetic field. Okay, that's all. Okay. The next solvent selection is given. Ideal solvent should contain no protons. No proton. That means all the proton will be replaced with a deuteron. Okay, or tritium, deuterium or tritium. Okay. And denatured solvents are used. Okay, deuterated, not denatured, deuterated solvents. Okay, deuterated carbon are used most commonly. Traces of ferromagnetic impurities cause severe broadening. Ferromagnetic impurities. Some substances will be having the ferromagnetic activity. Then because of that, what will happen? The peak broadening will lead to peak broadening. And next he is talking about the chemical shift. Of course, we know what is the chemical shift. Okay, then okay, see here, all of you, I will do one thing. Okay, the same thing. Okay, only few points will be different. Okay, you can read up to page number 4. Up to page number 4. Okay, don't go beyond that one because it will be more technical. Okay, you can't understand. Even the page number 3 also you can't understand. Spin coupling, multiplicator, spin system. Okay, that also you can't understand. Okay, maybe I will tell you what all things that you have to read. Only few pages. Like, 3 or 4 pages only I will give. Okay, just go through. If you are interested, you can read all these things. This is the entire abstract I have taken from that book. Which is my own notes. Okay, you just go through. You will have in-depth knowledge about what is NMR. Okay, then you have to read only 2 to 3 pages when it is sufficient for you. Most of the points are discussed already. Some points may be new. Okay, just go through the material. Okay, therefore with this we will try to finish this one. Okay, then we will go to the next topic, that is MS, next class. Okay, please absent today. Students, please absent today. Number 1.
Present, sir.
2.
Present, sir.
3. Number 3. Number 3 is absent. 4.
Present, sir.
Sir, 3%, sir.
No, who? 3% are.
Sir, 3%. 3.
Okay. 4.
Present, sir.
5.
Present, sir.
6.
Present, sir.
7.
Present, sir.
8. Number 8. 8 is absent. Number 9.
Sir, 8 was there, sir.
Okay, number 9.
Present, sir.
10.
Present, sir.
11.
Sir, she was there. Network issue. It
12.
left and she
12.
Present, sir.
13.
Present, sir.
14. Number 14. Absent.
Present, sir. 14.
15.
Present, sir.
16.
Present, sir.
17.
Present, sir.
18.
Present, sir.
19.
Present, sir.
Okay, all of you can leave. Okay, thank you.
Sir, ID 14 present.
Who?
Sir, 14, ID 14.
Sure, okay. All of you can leave. Okay.
Thank you, sir.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Thanks.
Thank you, Mama.